Morning, guys. My name is Zhang Haolin. Today, I'm going to talk about wavefront modulation and its application in laser optical trapping. So first of all, what is wavefront modulation? Well, we know that light is a wave, right? Into the wave, you have the phase information and the amplitude information. So imagine that this wave is passing through a certain phase configuration. The phase information is modified, and therefore the wavefront is modulated. In our case, we are looking forward to realize the dynamic wavefront modulation. So we are using a liquid crystal on silicon display. Well, this element is also referred as a spatial light modulator. And how a spatial light modulator works? Well, in this case, we can generate a certain phase configuration in the liquid crystal on silicon display. So the light passed through, or in this case, reflected by this spatial light modulator, is modulated. As we are looking forward to use such element to work as its best performance, we have to calibrate this element. In this case, we are calibrating two characters. First, the surface inhomogeneity, and second, the phase voltage response. For the first one, which is the surface profile calibration, we are generating a dynamic Sharp-Hartman pattern. And for the second case, we are generating a dynamic split lens configuration. So once this element is calibrated, we are using the element to realize laser optical trapping. Well, laser optical trapping is quite popular nowadays and is very useful, especially in the biological study. In fact, the principle of optical trapping is first proposed by Nobel laureate Dr. Stephen Chu. And just last year, Dr. Arthur Ashkin also won the Nobel Prize with optical tweezer. Well, within our scheme, we are using the spatial light modulator to generate a continuous split lens configuration. And from this configuration, we can have a bezel beam. And this bezel beam can be used to generate a light cone structure which is hollow inside. Now, imagine that you are putting a small microparticle inside this light cone structure, and it can be trapped according to photophoretic force. And now, let's come here to have a look at the experimental scheme. I'm using the green laser, and it is illuminating this spatial light modulator. In this spatial light modulator, the pattern or a certain phase pattern is generated. And therefore, in this arm, we have the light cone structure. It is located here at this position. And now, we are putting a container here, and inside the container, there are microparticles. And finally, by stepping the container, the particles are gonna fall, and it finally falls into the light cone structure, and it is finally captured. So this is our system, and we are going there to see how this system works. Well, here we have a video. Well, you can see this is the container, and we are going to play the video. So first of all, you see I'm stepping, and there is a particle trap. Let's have a look at this for the second time. So the container, tap, particle. So we are able to trap a microparticle, but is it available for us to manipulate this microparticle? The answer is yes. As we are using a spatial light modulator, we can dynamically change the focal length of this continuous split lens configuration. And once you're changing the focal length, the position of this bezel beam or the position of this light cone structure is changed. For instance, it can be changed from here to here. right? So the particle trapped into this structure, this LightCoS structure, is as well to be shifted. Let's have a look how its performance. So here we still have the particle trap, right? It is here. And now we are changing the focal of the structures and you see it is here now. It is gradually moved along this actual direction until it goes here. Now let's have a look at this for the second time. You see here the particle, and it is shifted through here. So the feasibility of our system to realize optical trapping is demonstrated. We are furtherly looking forward to use our system to perform more biological study. So thank you for watching.